Following up our initial video on the motivation to talk about limits, well, now it's time to talk about limits. In this video, we're going to introduce what the concept of a limit of a function is, particularly at a single point. And then in following videos, we will look at examples and also other topics relating to limits. So let's go. Okay, here we go. We got to dissect a lot of stuff here. Definition of the limit of a function at a point. Let's suppose that we got a function, call it y is f of x, and it is defined for all values of its inputs x, quote unquote, near x equals a, but not necessarily at x equals a. So it could be defined at a, but for our definition of a limit, we do not need the function to be defined at a, but we do need the function to be defined for values of x, quote unquote, near a. Now, when we say the word near here, we mean kind of arbitrarily close by on both sides. So if you think here is a, and these are all these different values of x, well, then what we're really saying is go close by on both sides of a as long as we are defined nearby, like so, but not necessarily at a, then that's what we need in order for us to talk about a limit. Okay? So that's first setup. Got the function defined for values of x near a, but not necessarily at a. If it is defined at a, that's also okay. Then, if this function f gets arbitrarily close to a number L, as x values get arbitrarily close to the number a, but not necessarily equal to a, then we are going to say the following, that the limit of the function f of x as x approaches a is this number L, and we write this statement right there. So that statement literally says this in quotes: the limit of the function f of x as x approaches a is equal to L, where L is some real number. So what is all this saying? And by the way, we're going to look at some pictures here in a moment to get a better visualization. But just think about what this says. The values of x are getting really, really close to a. Kind of go back up to the number line. So the x getting really close to a, like so, from both sides. But maybe not necessarily at the location of a. Just get really, really, really arbitrarily close. Then the function should be approaching something as well. Those are the output values. The function values are approaching some particular number L. So we can draw a little picture to help us visualize. Is that, I don't know, maybe my function looks like this. So you see, as we get close in the x direction to a, the function is getting really, really close to some number, output-wise, the real number L. And when that happens, we say that the limit of the function f of x as x approaches a is equal to the number L. And again, note, we don't have to be defined there, because all we're doing is getting arbitrarily close, not necessarily equal to that location. So this is the idea of a limit. And I want to show some diagrams of different ways that a limit could happen for a function as well. Now, when this does happen, when we have the limit of the function f of x as x approaches a is equal to this number L, then we say that the limit exists. That limit exists, and the limit is L. However, this might not happen, and we're going to definitely look at counter examples as well. If it doesn't happen, if it's not true, then we say the limit does not exist. Go figure. And what we would write is right here, we could write DNE for short. Limit does not exist, DNE. So either a function has a limit that exists or it doesn't exist at a location of x equals a. As we approach x towards a, the function should be approaching this number L. If that happens, a limit exists. If it doesn't happen, limit does not exist. So all this ongoing conversation in this portion of the introduction to calculus is all going to pertain to limits. And there's a lot of things that we have to talk about. This is just the beginning where we start introducing the concept. So here's a more fancy looking picture put together. And it's kind of like the one we saw that I drew a moment ago. And what it's showing is you got some function. That's the blue graph there. That's the function itself. And these little arrows in the x direction, these green arrows here, right? We're approaching the number a on both sides of a. And as we can see on the graph of the function f of x, we are approaching the output value of L. And even though the function is not actually defined at L, we don't care because we're talking about a limit, not the actual numerical value output of the function. We're just getting really, really, really arbitrarily close to the location of L. And in this case, the function is not defined here at A as indicated by the open circle or hole in the graph. So in this case, we would write that the limit as x approaches a of the function f of x is equal to L. And of course, the limit exists at this location. Now, in this picture right below, it looks almost like the one we just looked at. The only difference is in this case, the function f of x is actually defined at the location x equals a, and in fact, its output value is equal to L. Now, even though that happens, it doesn't change the fact that the limit exists, because all we're still saying is let x get really, really close to a from both sides, and the function is still getting really, really close to this output value of L. Only difference is now the function happens to be defined at x equals a, and it actually is equal to L, but that doesn't change anything from the previous graph. So whether or not the function is actually defined at the point doesn't change the fact if the limit exists or not. All we need is that from both sides of x, as we get really, really close to this number a, the function is approaching this output value of L. So again, in this case, limit as x goes to a of the function f of x is again equal to this number L, and the limit exists. Yet another thing that can happen, like in this diagram here, is that the function here is defined at a, but notice that dot right up there, right? That's its output value at a. It actually isn't the same location as what our limit is approaching. So you notice again, we're approaching x is a from both directions. And what's the function doing? It's getting arbitrarily close to this number L. Now, it doesn't have to equal the output value of the function like we see here, because all we're talking about for limits is that my function is approaching some particular output value as I get really, really close to the x location of a. And that's okay. So in this case, even though the output of the function is not the same location as the limit still exists at a. Limit as x goes to a of f of x is L. Limit exists again. And those are basically the three different ways that a limit could exist for a function being a real number L. Now compare that to this graph. Look what's going on here. Now this graph, it involves the concept of what's called one-sided limits, which we'll talk about in a couple videos from now. But notice what we're doing as we're approaching x is a on the left side of a. The function f of x is getting really, really close to this number m, let's say. We see it right there in the picture. Now as we approach x is a on the right side of a towards a, the function now is approaching this other location, n. And here's an example of how a limit could not exist. In this case, we would say limit as x goes to a of f of x does not exist, right? Remember, DNE does not exist. And that's because we're not approaching the same thing on both sides as x goes towards a. On one side, as I go to a from the left to the right, the function approaches m, as in mama. And on the other side, on the right side of a, as we go from right to left, the function is approaching this other number, n. Those two things don't match up. And because they don't match up, the function is not approaching a unique output value as we get close to the location x is a. And when that sort of thing happens, by definition, the limit does not exist because it's not approaching that unique number. Now, that's just one way a limit cannot exist. We're going to explore a lot of different ways as well. We can say there's a variety of things that can happen, specifically when we have vertical asymptotes and things like this. But that is your introduction to the idea of a limit. The following video, right after this, is going to discuss some examples. How can we find some limits initially? And from there, we will look at one-sided limits after that, and then get into conversation of limits involving infinity. So hopefully that helped introduce the topic of a limit for you. And then stay tuned for the next video where we look at some specific examples of finding some limits. The end. Till next time. Math and Beats.